Hello everyone. In this video, we see some solutions of previous year questions related to ordinary differential equation. The first question is find the singular solution of the differential equation satisfied by the family of curves beta square minus 2 plus d beta y minus x square plus 1 equal to 0 and beta is parameter. We know the singular solution not get directly from the differential equation or the singular solution not satisfy the differential equation. So how can we get the singular solution of the differential equation? The singular solution can be found by setting p discriminant or c discriminant condition. Okay, c discriminant in the sense the parameter c or beta according to the questions. Okay, so given beta square plus 2 beta y minus x square plus 1 equal to 0, when we differentiate this equation with respect to x, we get beta equal to x by y dash. So substituting this beta into the given equation, we get the equation x square minus 1 into p square minus 2xy into p minus x square equal to 0. So by using p discriminant condition, that means b square minus 4ac equal to 0, where b equal to minus txy, a equal to x square minus 1 and c equal to minus x square. So we get x square plus y square equal to 1. Similarly, when we consider beta discriminant or c discriminant condition, we get the same solution. So this solution is called singular solution. Okay, so in similar way, when we consider the differential equation of the form the differential equation satisfied by the family of curves c square plus 2cy minus x square plus 1 equal to 0, where c is parameter, using similar method we get the solution x square plus y square equal to 1. Okay, this is a singular solution. So next, Wronskian solution. The question is, show that the solutions e to the power x, e to the power minus x and e to the power 2x of the differential equation d cube y by dx cube minus 2 d square y by dx square minus dy by dx plus 2y equal to 0 are linearly independent on every real line. Okay, so Wronskian determinant, and the property of Wronskian determinant gives us is y w of y1 y2 y3 not equal to 0 implies the solutions are linearly independent. Okay, so the Wronskian determinant for three solution y1 y2 y3 is given by determinant y1 y2 y3 y1 dash y2 dash y3 dash and y1 double dash y2 double dash and y3 double dash. So using the given y1 equal to e to the power x, y2 equal to e to the power minus x and y3 equal to e to the power 2x, we get w equal to 6 e to the power 2x, which is not equal to 0 on every real line. Okay, that means the solutions are linearly independent. So now we see some definitions related to linear dependence or linear independence for any function. The set of functions f1, f2, f3 dot fn are said to be linearly dependent on an interval ab if there exists c1, c2, c3 dot cn not all 0, such that c1 f1 plus c2 f2 dot plus cn fn equal to 0 for all x belongs to a comma b. And when the c1, c2, c3 cn are all 0, we say that the functions f1x, f2x, f3x and fnx are linearly independent. Okay, so using the linear dependence independence property and the Wronskian determinant, we can find the solution of the next equation. Next question, let y1 and y2 be two solutions of the problem d square y by dt square plus a dy by dt plus b yt equal to 0 for all t belongs to R, where y 0 equal to 0 is the initial condition, where a b are constants. So question is find the Wronskian of y1 and y2. The Wronskian wt of two functions y1 and y2 is given by determinant y1 y2 y1 dash and y2 dash. So for the second order linear differential equation of the form d square y by dt square plus b dy by dt plus qt yt equal to 0, and Abel identity states that the Wronskian satisfies wt equal to c into e to the power minus pt dt. Okay, so in this problem pt is constant, that means we get wt equal to c e to the power minus at. So using the initial condition y0 equal to 0, we can say that y1 0 equal to 0, y2 0 equal to 0. Okay, and if we need taking derivative on y1 dash at 0, we get when y1 dash 0 and y2 dash 0 are not given, using the value of y1 0 and y2 0, we can directly find that w0 equal to 0. So substituting the t equal to 0 in the Abel identity, wt equal to c to the power minus at, where t equal to 0, we gain capital C equal to 0. That means the Wronskian wt equal to 0 into e to the power minus ad, that is wt equal to 0. So wt equal to 0 is the value of the Wronskian. Okay, so next question is, let x1 x2 dot xn are linearly independent solutions of a0 t xn plus a1 t xn minus 1 plus an tx equal to 0, where a0 not equal to 0 for any t belongs to I, and a0 a1 an are continuous function on an interval I for t0 belongs to I. Question is prove that w x1 x2 xn t equal to w x1 x2 xn t0 exp minus integration t0 to t a1s by a0s ts. Okay, so before proving this theorem or answer, at first we see some basic properties of uh, derivative of determinant. Okay, when you consider 2 by 2 determinant w x1 x2, we see that w x1 x2 dash minus x1 dash x2. When we differentiate with respect to t, we get w dash equal to x1 dash x2 dash plus x1 x2 double dash minus x1 double dash x2 minus x1 dash x2 dash, which implies x1 x2 x1 dash dash x2 double dash in determinant form. Okay, and for third the determinant, we see that wd dash t equal to x1 x2 x3 x1 dash x2 dash x3 dash x1 triple dash x2 triple dash and x3 triple dash. Okay, so now we consider the general differential equation, and since a0 not equal to 0, so by dividing a0 we get xn equal to xn plus a1 by a0 xn minus 1 plus dot n by a0 x equal to 0. If we consider pi equal to ai by a0, that means p1 equal to a1 by a0, pt equal to a2 by a0, and so on. So the above equation becomes xn plus pn xn minus 1 plus dot plus pn x equal to 0. Okay, and we shift all the terms except xn, we get xin equal to minus p1t xn minus 1 xin minus 1 minus dot minus pn xi. Okay, and if we define the Wronskian wt equal to x1 x2 dot xn x1 dash x2 dash dot xn dash dot and x1 n minus 1 x2 n minus 1 and dot xn n minus 1. So when we taking derivative of the Wronskian, that means Wronskian derivative or derivative of the Wronskian is sum of n determinants where in each term only one row is differentiated. That is w dash t equal to x1 x2 dot dot xn, and the lower last row becomes x1n, x2n and xnn. And substituting the value xin into the last row, we get the Wronskian determinant, derivative of the Wronskian determinant. Okay. Using the linearity property of determinant, we can break the last row into sum of determinants. Every term involving p2, p3, p4, pn multiplies a row that is already identical to one of upper rows. So first through n minus 2 rows, making those determinants 0. So we can get only one term containing minus p1 xi n minus 1. So therefore w dash t becomes of the form. Okay. We only take common p1t from the determinant, and the from the last row we get w dash t equal to minus p1 and the determinant form. So the determinant is same as the Wronskian determinant. That means w dash t equal to minus p1 wt. The w dash t means dw by dt. Okay, when you put the value of p1, we get wt equal to wt0 exp minus t0 to d1s by a0s ds. Okay. So next we can prove another theorem. When phi1, phi2, phi n be fundamental solution set of the solution, fundamental set of solutions of the homogeneous linear vector differential equation dx by dt equal to atx, and let phi be an arbitrary solution of the above equation on AB, then prove that phi can be represented as a suitable linear combination of phi1, phi2, phi n. That is, there exist numbers c1, c2, cn such that phi equal to c1 phi1 plus c2 phi2 plus cn phi n. That means phi is the linear combination of phi1, phi2, phi n, also solution of the differential equation. Okay. So before proving this theorem, we see some definitions related to n order linear differential equation. The general ODE or ordinary differential equation of order n of the form LU, where L is the linear operator. Okay. And when you consider this in the general form, in the third form, that means p0 dny by dxn p1 dn minus 1 y dxn minus 1 plus dot 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 plus pn y equal to rx. This is the general form of linear differential equation where p0 not equal to 0. Okay. And if we consider the second order and simple second order linear differential equation, and we know the e to the power rt or e to the power mt is the trial solution. When you consider the trial solution of the equation and substituting this trial solution into the equation, we get r equal to minus 1 or r equal to minus 2. Therefore x1 equal to e to the power minus t and x2 equal to e to the power minus 2t. Okay, each satisfies the differential equation. So when you consider an arbitrary constant c1 and c2, the function xt equal to c1 e to the power minus t plus c2 e to the power minus 2t is called linear combination of x1 and x2. Okay. So this calculation illustrates an important property of linear homogeneous equations, that is called principle of superposition. If two functions are solutions of the linear homogeneous differential equation and they are linear combination of two functions, is also a solution of the differential equation. Okay. In similar way, we consider the general differential equation in second order, and phi a2 t y double dash plus a1 t y dash plus a0 t y. And if we consider phi 1, phi 2 are solutions of the differential equation and c1, c2 are arbitrary constant, therefore phi t equal to c1 phi 1 plus c2 phi 2 also the solution of the equation. Okay. By using linear property, we can directly solve or directly check that equation. And if we consider and n solution, that means u1 u2 um of the linear differential equation of order n, then u equal to c1 u1 c2 u2 and cm em also the solution of the equation. Okay, these are both called the principle of linear superposition or principle of superposition. Okay, so now we prove the theorem. Since each phi k is a solution of the differential equation dx by dt equal to tx, that is d phi k by dt equal to at phi k satisfies, that means phi k satisfies the differential equation. Now we consider the summation form, that means we consider the phi, that is d dt of summation k equal to 1 to n c k phi k. We know that the derivative is distributive, derivative is distributive, that means summation d dt ck phi kt, and ck is constant, so ck can be taken out from the derivative, so summation k equal to 1 to n ck d dt of phi kt. And from the above consideration d phi k by dt equal to at phi k, so we can replace this d dt of phi k by at phi k. Okay, therefore we get at into ck phi k, that means d phi by dt equal to at phi on t belongs to a comma b. So phi satisfies the differential equation, that means phi equal to c1 phi 1 plus c2 phi 2 plus cn phi n is also solution of the equation. Okay, next is linear system of differential equation. So the question is, if the n vector functions phi 1 phi 2 dot phi n defined by phi 1 is a column vector, phi 2 is also column vector, dot phi n also column vector, are linearly dependent on a less or equal to t less or equal to b, then their Wronskian vanishes for all t on ab. Okay, so before proving this theorem, we see some basic properties of linear systems. If we consider the system of differential equations of x1 x2 dot xn, this can be write in more compatible form, that means dxi by dt equal to summation nj equal to 1 to n aij xj. Okay, now the system of linear differential equations of n unknowns x1 x2 x3 dot xn of the form dx by dt equal to atx plus ft, where at is the n by n matrix and x and ft are column vectors and t is the independent variable. Okay, so if we find the fundamental matrix of the homogeneous system dx by dt equal to at into x, then the solution is given by phi equal to r to the power lambda t, where phi is given by the fundamental matrix. Okay, the above system of differential equation dx by dt equal to atx plus ft, where ft is, if ft not equal to 0, this system is called non-homogeneous, and if ft equal to 0, this system is called homogeneous system. Okay, so now we prove the theorem. Since the vector phi 1 phi 2 phi n are linearly dependent, so there exist n numbers c1 c2 cn not all 0 such that c1 phi 1 plus c2 phi 2 plus cn phi n equal to 0 for all t belongs to a comma b, which corresponding to the components reduced to summation cj phi ij equal to 0 for all t belongs to a comma b. Okay, and I equal to 1 to n. So in particular for the point t0, we must have j equal to 1 to n summation j equal to 1 to n cj phi ij t0 equal to 0. Okay, so since the numbers c1 c2 cn are not all 0, and we know that the system of equation, um, that means the system of equation That means C1, C2, C2, Cn are not zero solution gets only from the coefficient determinant equal to 0. Okay, and this coefficient determinant becomes the Wronskian at t0. Since t0 is arbitrary, we must have w of phi 1, phi 2, phi n t equal to 0 for all t belongs to a comma b. Okay, and next we prove the opposite theorem. If n vector functions phi 1, phi 2, phi n defined by phi 1, phi 2, phi n are n solutions of the homogeneous linear vector differential equation dx by dt equal to atx, and the Wronskian w at the particular point t0 equal to 0 for some t0 a belongs to less or equal to t less or equal to b, when phi 1, phi 2, phi n are linearly, then phi 1, phi 2, phi n linearly dependent on ab. Okay, so consider the algebraic system, and because we already see this type of expression summation j equal to 1 c j phi j t0 at 0 in the unknown c1, c2, cn. Okay, so this system has non-trivial solution because the coefficient determinant equal to 0 at t0 equal to 0. Thus there exists c1, c2, cn not all 0 such that c1 phi 1, c2 phi 2 plus dot dot cn phi n t0 equal to 0. Okay, if we consider phi equal to c1 phi 1 plus c2 phi 2 plus cn phi n for all t belongs to ab, since phi 1, phi 2 dot dot phi n are solutions of the differential equation dx by dt equal to atx by principle of superposition, phi is also the solution of the equation dx by dt equal to atx. But the function phi t0 equal to 0, we considered that. So according to the existence and uniqueness theorem for the linear differential equation, a homogeneous system with initial condition of 0 at point has only the trivial solution phi t equal to 0 for all t belongs to a comma b. Therefore c1 phi 1 plus c2 phi 2 plus cn phi n equal to 0 because phi equal to 0. So this condition connected with the linear algebra, that means linear combination equal to 0 implies what? Since constant c1, c2 not all 0, so the vector functions are linearly dependent on ab. Okay, okay, thank you, bye bye.